Good afternoon, everybody, and welcome to your first theoretical lecture on structural equation modeling. The purpose of this lecture series is kind of like to take you through the theory behind structural equation modeling, and I'll take you through every step of the way, don't worry. By the end of this little lecture series, you'll be able to manage everything quite well, I think. My name is Llewellyn van Zyl, and I'm an assistant professor at the Technical University of Eindhoven. And I work with M+, and I work with structural equation models every single day of my life. And I want to share with you how to approach one, how to estimate one, how to compare different models with another, and how to just become the best possible researcher that you possibly can. So during the next couple of lectures, we'll be doing 4 things. So today, we're going to reflect a little bit upon what you already know about structural equation modeling, what you already know about regressions, right? Once we have that, I'm going to take you through a gentle introduction into structural equation modeling. So just the basic concepts, step-by-step guides, so you have a thorough understanding of what to expect in the next section. In the next video, we will then specifically focus on how do you estimate these models? How do you compare? What's the process? There's a 5-step process that we follow. How do we get from idea to results? And I'll take you through that. And finally, we'll take you one step further, and I'm going to show you what is mediation or indirect effects from the structural equation modeling perspective. So after watching these 3 videos, there's 3 things that will happen, 3 things that we hope you will learn. First one is really have a very deep understanding of structural equation modeling and its value in relation to the normal general linear approach. We're going to show you how to differentiate and compare different measurement models with one another, and what's the difference between measurement models and structural models. And finally, I'm going to show you the basics of mediation. Okay, so I'm going to show you that you guys already know quite a lot before you even started the structural equation model. And I'll take your hand and we'll walk through this step by step, promise. So let's kind of like look at what you already know. So let's take a little bit of an homage, a little bit of a reflection on normal multiple regressions. So I utilized a paper that I did very long ago in 2010, and the basic idea behind this paper was that we wanted to look at what predicts work engagement of industrial psychologists. We had an assumption to say that work role fit, so me as an individual, do I fit the role that's required of me? If there's a match between the person that I am and the work that I do, I'm going to be more engaged. Also, if I find meaning in my work, so if I see that my work contributes to something bigger, will that lead to engagement? And again, this is theory orientated. So we did normal regressions, stepwise regressions. We kind of have our descriptive statistics here. It was on a scale of 1 to 5, I think, where 1 being the best and 5 being the worst. So here we see work role fit 1.9, so basically 2. That's quite good. Same with meaning, close to 2, engagement quite good. So people are quite good. High levels of engagement, high levels of meaning, and high levels of work role fit. We look at the skewness and kurtosis. As you can see here, they were normally distributed because they were smaller than smaller than 1. But what's important for us, the first thing is to look at the relationship between the factors. Here we see there is a relationship between all of the factors. They're very high, very strong, and they are significant. So that tells us, the combination of these 2 things tells us that we can actually do a regression. So we put all of these things into SPSS, and this is the results that we got. So overall, we found that meaning and work role fit declares 55% of the variance in engagement. It's quite a lot, actually. And there's also our fit statistic and the amount of degrees of freedom that we had. We found that our overall regression, the difference between our null model and our actual model, there is a significant difference between the 2. So yes, The nested and unnested models are significant, therefore we can move on. Now, we have to take all of these things kind of into consideration, and then we plot this on a nice diagram. So the actual standardized coefficient, so the strength of the relationship is significant. So the strength of the relationship between work role fit and engagement is 0.22. And the strength of the relationship between meaningfulness and engagement is 0.54. And both of them together declare 55% of the variance in work engagement. Great. We have an amazing model. But what are some of the limitations of this approach? So this is what we call the ordinary least squares approach. And one of the big things here is that we lose a lot of variance when we try to estimate it, because there is things that's going on between these two factors. There is interaction effects. There are things that's happening here, but we're not capturing them with normal regressions. We're also not capturing error. So there are a bunch of factors, there are a bunch of things that kind of make this an obsolete approach. So another major factor for us is that how do we get to these factors in the traditional approach? We take all of the items, so all 5 items that loaded on work role fit, we added them together and divided them by 5, and we got a mean score for that. That's how we got to this score, and we do the same for each one of these. What's the problem with this? So this is kind of how that would look like in practice. So we've got 4 items that we asked people on a scale of 1 to 5, 1 being the best and 5 being not. Regardless of what you are doing with your time, do you feel time passes by quickly? I'm always very absorbed in my work. I love what I'm doing, and my life is too short to postpone pleasures. So if we look at it from the general least squares perspective, we see that the mean score for all of our participants on this item was 4.7, the mean score 4.9, so on and so forth. The item loading was 0.73, 0.77, 0.62, and 0.61, right? This is the factor loading that you will be familiar with. Now, like I mentioned, when we want to get to this happiness factor, right, we want to create it, we say item 1 plus 2 plus 3 plus 4 divided by 4 gives us happiness, right? Makes sense. What's the problem? We assume, when we do it that way, that each one of these items loads exactly the same on that factor. And unfortunately, it doesn't. Even though the mean scores would stay the same, the item loadings, the factor loadings, are not equal. Therefore, you can't say that this plus this plus this plus this gives us that factor, or divided by 4 gives us that factor. We have to take this into consideration. And the general least squares or the ordinary least squares method, unfortunately, does not do that. Now, I'm going to go over to the next slide, and I want to show you what happens if I estimate exactly the same thing, this confirmatory factor analysis in M+. So I'm utilizing structural equation modeling. Now, the things that's going to happen is I'm going to add error to each one of these items. And let's see what happens to the mean score and the factor loadings. Item loading stays exactly the same, but now you see the factor loadings. So the mean scores stay exactly the same, but now the factor loadings are different. See, GLS 0.73, 0.75, 0.77, 0.8, 0.62, 0.6. So you see that there is a major difference between these two approaches, because this approach also takes into consideration the interrelationships between these factors, and that's important. The estimated mean score here is 4.31, where here it's 4.62, so it's a bit lower. But when we use SEM, we can't really have an actual mean score because our actual mean score is 0, because we're more focused on the correlation, the covariance matrix, and the interaction than we are with the mean scores. But I estimated just to kind of show you. Okay, but now how do we compensate for this? What do we do? Well, we utilize structural equation modeling, and this solves all of our problems. So what is structural equation modeling, right? So basically, it's it's not a specific technique, right? It's not one single technique. It's basically a series of different types of multivariate statistical techniques that we utilize to analyze and estimate very complex multiple relationships between factors. So unlike normal regressions where we have factor one, then we set the next factor in to our regression equation and so on and so forth, we look at all of these relationships and things together. So it's an integration of different approaches. So we utilize item response theory, for example, like I showed you in the earlier slide with the different loadings. That's item response theory. So we include that. We look at everything from latent profile things to regressions to correlations to etc. So it's an integration of all of these things together. What makes it different? It's a confirmatory approach rather than an exploratory. So we have a theoretical idea about how these things work, the relationships between different factors. So we don't throw all things into the big statistics pot and pray that something positive comes out. We have an idea of how these things work, and we're testing theory against our data. We don't let our data dictate to us what it is that it thinks is the best. Structured equation modeling also helps us. It specifies systems of relationships, right? So it's not just a relationship between A and B and A and C. It's a relationship between A and B with C and B and C with A. So it's combinations of relationships rather than specific relationship at a time. What makes this also a lot different than normal approaches is that we're estimating what we call unobserved factors. We're estimating latent factors from things that we've actually measured, right? So we're creating things out of measured variables. So out of those items, we create happiness, but they don't necessarily measure happiness. The items together measure happiness, but each item in itself doesn't. So from the combination of these things, we create something that doesn't exist, that's unobserved. We measure something that you can't see. And finally, what's really important here is that we're basically testing different forms of the theory against our data. Okay, does it make sense? So to summarize, structured equation modeling is not a specific technique. It's an integration of techniques that we take from psychometric theory, factor analysis, latent variable analysis, path analysis, regressions, simulation studies, and etc. It's an integration of these things that help us to estimate the systems of relationships between factors. Okay, so where do we utilize this? How can we utilize it? So primarily it's theory testing, right? So it's hypothesis testing over a theory, and we test our data against it. We can estimate mediation or indirect effects if we want to know how a factor translates. So how we know that work role fit leads to happiness and happiness to performance. But we want to know how does work role fit indirectly affect performance through happiness. So we know that work role fit declares maybe, let's say, 50% of the variance in happiness, but how does that amount of variance, that impact that work role fit has on happiness, how does that specific impact have influences task performance? So that's mediation. We can look at group differences, so we can look at how males and females respond on our model, so maybe the relationships look different for them for some reason. We can look at longitudinal relationships, and we can look at it from a multi-level perspective. But all of this is underpinned by latent variable modeling. And latent variable modeling is, again, taking observed things that we've asked, and we're estimating something that doesn't exist. So this happiness in our thing doesn't exist, but it's a combination of these different factors. So we ask these questions. Based on these questions, we create that happiness thing that is unobserved. It doesn't exist practically in our data. So what are some of the advantages of structured equation modeling over the ordinary least squares method? So, of course, it's a lot more flexible in its application. You can do a lot more with it at once than you can do in SPSS, for example. Unlike the general least squares method, we really focus on the estimation and incorporation of measurement error, so the noise that's happening in the system. This happens as a byproduct in GLS, but it's an active consideration in our SEM process. We also test multiple relationships and interactions simultaneously, unlike the GLS method where we take one factor to our one independent variable to our dependent variable, then a next IV to our DV, then the next. And like that, we look at all of these things together and we model these things simultaneously, which is important because then we can estimate the flow of information between our different factors. Like I also mentioned previously, we examined this latent factors as a function of our observed factors. It provides us with a more accurate or improved statistical estimation. So it's more closer to reality than you would do if you just did it with the normal GLS method. It also helps us to remove a lot more of the random error of the noise because we're estimating it. We're also incorporating it into our model. And it also helps us to find the best model for our data where the GLS method doesn't do so. Okay, so that's some of the advantages of the model. Now, what are some of the key things we have to consider when we want to utilize SEM? So there are some key aspects. So the first thing is we always specify what we call a priori models. A priori models are theoretical models, theoretically informed models. And we always specify the full model. So we don't, in a normal GLS method, we would do an EFA, exploratory factor analysis on work role fit scale, and then we'll do one on the happiness scale, and then we'll do one on the performance scale. And then based on that, we then create the means, and then we actually do our analysis later. In SEM, we do all of these things together. They must always be on the same proverbial page. You can't have this do a validation of an instrument, so a CFA, confirmatory factor analysis on the one factor, and then the other factor, and then the third factor, and then put all of the things together. No, they're always together on the same page. You always estimate them together. And they're all theory-based, right? So you can't just thumbsuck something out of your thumb. You have to have a very strong theoretical argument why these things are in place. The next assumption is that your data needs to be normally distributed. In more advanced programs like M+, for example, you can utilize other estimation methods to kind of compensate for issues with normality. But if you utilize Lizrel or AMOS or some of these more rudimentary packages, you have to ensure that your data is normally distributed because you can't change the estimation method. Okay? So you can transform your data or something. A big thing with structured equation modeling is, unfortunately, it's sample size and model complexity dependent. You need a very large sample size to get this model to work, right? And you have to do what we call a power analysis. So you can go to, there's a website, I'll link it in the description, but there's a website you can go to, or you can utilize G-Power, and you can enter your items, the significance of the effect that you want, the alpha value, and you can get a good indication of how many people you need for your model. Now, unfortunately, it's also, even if I've got a very large sample size, model fit, so does my data fit my model, is very dependent on how complex it is. We know one of the limitations of the model is that, of structured equation modeling, is that if you have a very complex model, your data is automatically going to fit. You're going to automatically get a lot better fit. It's not necessarily it means that you get a better model, but or better fit for your theoretical model. It just means the more complex the thing, the more likely you are to get fit. But just because you have fit doesn't mean it's the best model for your data. Another factor that we have to assume is that our residual variances, so the error that our items provide, needs to be small and as close as possible to zero as you possibly can. Large residual variances, so that's the error in each item that we measure. If it's large, there's a big issue in your specific item. You have to figure it out. Another key assumption that I mentioned before is that we test different models and we compare them against each other. The major strength of this approach. And finally, is that we have certain criteria that we utilize to evaluate if a model fits the data. So we look at what we call model fit statistics. And there are certain criteria that we utilize to figure that out. But we also look at what we call measurement quality. So we look at specific item loadings. Is our questionnaires reliable or not? So there are some other factors that we utilize that we look at in model fit, in measurement quality. So these are the 6 things that you have to consider when you want to utilize SEM. So we basically, in SEM, we have 2 major types of models. The first model is what we call the measurement model, and this is basically correlational in nature. I'll explain what these things kind of like mean in the next slide. But this means like there is a bivariate relationship or covariance between all of the different factors, right? So, and we have different versions of this. So we don't specify what relates to what. We just specify how each factor is made up of which items. That's our measurement model. That's the model that tells us which theoretical model could physically perhaps match our data the best. Once we find the best fitting measurement model, we transform it into what we call a structural model. Now here you'll see this is correlations. We've changed this into regression. So this is directional. So because theory tells us that demands impacts engagement, and engagement impacts task performance. So as soon as we add that into the equation, it automatically also estimates error terms for these other latent factors. Okay, measurement models, correlational, structural models, regressions, direction. So just to summarize, measurement models, we're interested in the relationships between latent variables and its measured observed indicators. So we're interested in the relationship between these factors and between the factors and the items. Regressions, we want to specify directionality in the relationships. So through what we call this path model, this is the path model, so A leads to B leads to C. So you want to specify directionality between the different factors. In structural equation modeling, there is certain conventions, certain things you need to be aware of, okay? So it's how we draw things is very important here. In any model that we draw, a square means it's an observed indicator, right? It's an item or something or a mean score. It's something that we actually observed. A circle is what we call a latent variable, right? Dual arrowed arrows like this is what we call it indicates a correlation. And if we have an arrow that shows just one way, that is a regression, okay? Straightforward. Squares observed, circles latent, dual arrows correlation, regression one arrow. Let's see what this looks like. So this is an example of a path model, structural model, in structural equation modeling, right? So here, as you can see, the little blue ones, these are what we call observed indicators, and this is the items, the questions that we specifically asked, right? So this is the exact questions that we asked for each participant. These little green ones are what we call latent variables, and they're made up of these specific blue factors, these items that we've estimated. These little red things, right, is what we call the error terms, or the noise in each one of the items. So every item that we ask, it's not like 100% of the people are going to answer it in 100% the same way. We're also estimating like the noise. So some people might have answered difficult, some people might have seen it a little bit different. So there's always some error in everything that we measure. So that's what the little squares are for. The little circles are for. So unlike your normal GLS method, we have different words for independent and dependent variables in structural equation modeling. So here, for example, we have an exogenous variable. So this will be traditionally called our independent variable. I always remember it by saying exo, so it's kind of like beginning. So our exogenous variables are factors are basically equivalent to independent variables in the GLS method. Our endogenous factors are the factors of the outcomes of the interactions that we have to predict. So competence will be an endo, engagement would be an exo for that, and performance would be an exogenous variable. We know an exogenous variable also because as soon as we enter it, it automatically generates its own residual variance. Competence would not have one because here we're predicting, competence predicts engagement, right? And it doesn't predict it 100% and all of the variance. So let's say it predicts like 50% of the variance, but there's also some noise there, right? And that's why we get this residual variance there. And that's how you know it's an endogenous factor. Another thing you will notice is that each error variance, the residual variance, is constrained to 1, right? So the loading of it is all equal for everybody. You also notice that each one of these item loadings is constrained to 1. So the item loadings are fixed to 1. Why? Because it helps us to estimate other factors. So if we want to get a standardized value, we need something to be constrained to be a standard, a constant, so that we can generate standardized values. And M+ and all these other techniques do it automatically. So the first item in your loading will always be constrained to 1. Okay, that's automatic. This is important for in a bit. Okay, now that we have a basic idea of some of the concepts in SEM, you have different types of what you call path models. So this is a path model, right? But there's basically 3 types. We have the confirmatory factor analytic approach. We have what we call a latent path model, and we have an observed path model. Okay? So the confirmatory approach, here we are basically interested in understanding the relationship between the observed factors, so these items, item 9, 8, and 7, with its latent factor, right? So we are interested in understanding the relationship between the observed indicators and the associated latent factors. It's confirmatory. Why? Because the model is based on an a priori theoretical assumption that we have. From this perspective, we know that the MANS is made up of these 3 items, and that's what the theory tells us. That's why it's a confirmatory approach. We can also estimate a normal path analysis with observed indicators. And this is kind of like we've done in the initially we did the regressions. We have work role fit predicts meaning, and meaning predicts work engagement, but they're squares, so they're meaned out here. In this case, unlike the other approach, we can only estimate the structural model. Unfortunately, we don't have different measurement models to compete. We only have the structural model. We are only interested here in the relationships between the constructs represented by the direct measurement thereof. So we're only interested in the specific relationship between, or the combination of the relationships between work role fit, meaningfulness, and engagement. So in other words, it's basically just a series of multiple regressions, but put together in an equation. Okay? So the latent path model is incorporating this, the observed, and the CFA approach, right? So here we basically simultaneously test the relationship between the measurement models. So this is a measurement model, this in its own is a measurement model, and that in its own is a measurement model. So we simultaneously test the relationship between those measurement models and the structural model. So that's the combination of competence predicting engagement, predicting performance. Okay, does it make sense? So we're basically doing the CFA and the previous one all together. So this approach is really awesome. Why? Because it specifically incorporates the relationships between the observed and latent variables. So in other words, the measures and the factors. It also looks at the relationship between the latent factors themselves. And finally, it incorporates and compensates for the residual error, the residuals. In other words, the noise in the model. So this is what makes this approach so freaking amazing. Okay, so those are the 3 different models that you can estimate, path models. So in order for us to estimate this, there's a certain flow that we have to get to our final structural model, because the structural model, that path model, this one, is what we are basically working towards. This is the one that we actually want, but there's a certain process we have to follow to get to this final outcome. And I'll go into a lot more detail on this in the next video lecture, but fundamentally there is a 5-step process. Firstly, we have what we call model formulation. So in structural equation modeling, because it's a confirmatory technique, it needs to be based on a very fundamental theory. So we have to really figure out what is the underlying theory that we want to test. SEM needs a model that declares the relationships between the factors. So you have to have this before you even start with your data collection. Once you have this, we have a model that we need to test needs to be identified. So we look at model identification. Here, models need to have enough what we call pieces of information in the actual model in order to help us to estimate the stuff that's unknown. So that latent variable that's there, but it's not measured, we need enough degrees of freedom, enough pieces of information to be able to help us to estimate that. Okay, once our model is identified, we have what we call model estimation, and this is actually you doing the actual evaluation. So here we try to minimize the differences between the observed and the implied or latent factors, right? So we try to get a good match between trying to incorporate as much as possible. So we say as much as possible in as little as possible words. So we predict as much variance as possible with the least or the most complex model that we kind of have. And we utilize like an iterative process to get there. So we estimate what we call a nested and an unnested model, so something that's least restrictive to more restrictive and seeing which one fits the data the best. Once we have this, the fourth step, and this is where the measurement modeling strategy ends, we have model evaluation and modification. Here we want to assess the model fit. So the model that we have, we want to assess it against our data. And we have certain criteria that we utilize to do this, so certain tick boxes that you have to look at. We look at certain fit statistics, and we look at measurement quality. We also look at what we call absolute fit and comparative fit. So does the model actually fit its data, right? And comparative fit is like, now that we see that our model actually fits, how does it compare to our other models that we have also estimated? Because we want to figure out what's the best. Based on this interaction between these four factors, we finally create our structural model. And the structural model is the one that tells us A leads to B leads to C. That's the thing that we're interested in. So now that we have a structural model, that's of course the outcome, but we can do a lot more with the structural model. We can do mediation and moderation analysis. We can do multi-group, where we look at how the model looks like for different groups. We can look at changes over time. So how do people change over time? How do they grow? We can look at longitudinal confirmatory or causality. We can look at the underlying profiles that's in this thing and the underlying classes. So there is a lot of kind of like things in place that this approach can do. So I really hope, that you learned something from this lecture, and that you have some basic understanding of, structural equation modeling. Ladies and gentlemen, thank you so much. In the next lecture, we're going to a lot more detail on how to estimate these models. Have an amazing afternoon.